Thank you all for having me here. It's my great pleasure to be back in Santa Cruz and tell you this year about the formation of little red dots using the so-called self-interacting dark matter paradigm. So I tend to put my studies in the bigger context of galaxy dark matter halo connections because it's a long-lasting interest of mine. And the whole game is all about studying why the morphology of the galaxy sitting at the potential minimum cares about the large-scale distribution of dark matter. I mean, large scale is really an overstatement. It's distribution of dark matter within the virial radius. How come this halo structure determines, to a large extent, the galaxy morphology and structures? And last year, I told you about this story about the giant boundless disks in the context of the disk formation, the halo structure connections. And this year, I'm turning my focus into the other end of the extreme, little red dots, right? So these are the most compact extreme systems. So this kind of extreme systems are always always interest me because I think they provide us valuable stress test opportunities or pressure test opportunities to test our understanding of galaxy halo connections. So if this rings a bell, we can talk offline about our theoretical interpretation of this giant boundless systems. So, okay, moving on to my main story today. I'm going to address little red dots, and this is my operational definition. I regard them as almost naked supermassive black holes at redshift above, slightly above redshift 5. And this is largely based on my observational colleagues. Right? So these here, they show that in 8 out of 8 examples, the little red dots are consistent with just a point source convolved with a point spread function. And in this talk, I'm going to argue that extreme morphology is largely originated from the dark sector, and the little red dots are no exception. And in the self-interacting dark matter paradigm, they are the outcome of the core collapse of ICIDM halos. So the ICIDM self-interacting dark matter physics is really simple. Okay? It's regulated by the single key parameter, which is the cross-section, and the halo just evolves in 2 stages. The first stage, if you start from an NFW profile, as indicated by the red line here, okay, the first stage is the establishment of an isothermal core, as shown by this olive line. So I have a complete isothermal core in the center, which can be very large as probably the scale radius of the halo initially. And after a while, the halo would co-collapse. Right? It would co-collapse into a more cuspy configuration. And the central part, if you run the system for long enough time, or if your cross-section is really high, so you can reach maybe a state where the central part is a nuclear star cluster, or even a black hole. So this cartoon illustrates the power of ICIDM paradigm. Essentially, it's introduced to accommodate a lot of the dwarf galaxy diversity problems, right? You have ultra diffuse, you have ultra compact such relics of a nuclear star cluster with an envelope experiencing tidal stripping. So in the isothermal core stage, this system would be an ultra diffuse galaxy. And in the core collapse stage, you can produce a lot of the nucleated dwarfs, which arguably accounts for 40% of the local dwarf population. But via very careful relativistic calculations, people like my collaborator here, Michael Feng, he can show you that at the end state of ICIDM evolution, basically the central density decreases in the isothermal core building stage and increases again until it reaches the black hole seeding stage. This is called the core collapse, bravothermal core collapse. But eventually, this black hole seed mass can be up to 1% of the total halo mass. And that 1% is not sensitive to halo mass or concentration or the halo profile to begin with. And it's essentially the total mass within the so-called short mean free path regime, if that jargon talks to you, okay? But you have to trust me on that, 1%, about 1%. I don't really care if it's 1% or 0.1%. You will see shortly. If core collapse occurs early enough before reionization, then naked black holes can arise, right? This halo has no stars yet. And If the cross-section is high enough, if the core collapse is fast enough, then you can see the massive black hole out of 1% of the halo mass. That's a very efficient seeding mechanism. So I realized that Fabio yesterday categorized our scenarios into this exotic model. Okay? I don't know if it's a good word or not, but let me argue it's not personal, Fabio. It's just for stage effects. Okay, so it's not exotic. At least it's not more exotic than CDM. It's just a different side of the same coin. If you consider Yukawa-like interactions, so CDM and ICIDM are just at the two ends. So CDM has large coupling factor and very small. CDM has small coupling factor and large mediator mass, and ICIDM is just the opposite. And the cross-section has to be velocity dependent, characterized by a rest frame or zero velocity cross-section, which I will call sigma naught or sigma naught m. And there's a velocity scale omega above which cross-section decreases sharply. This is both a particle physics argument, but also an astrophysical need, because you don't want large cross-section effects for, say, galaxy clusters. Right? We want very minimal self-interaction effect for massive systems. Okay, and the key quantity we consider here is the core collapse timescale. Okay? We want to see the black hole by redshift 5. Say, okay, you have a limited time budget to work with. So we want to consider the core collapse timescale. And the core collapse timescale at a given redshift is just a function of halo mass, halo concentration, and the cross-section parameters I just mentioned. You can consider these two as a one parameter, effective cross-section indicated here. So how to interpret this? So suppose we consider a halo, okay, at redshift 8. We want to explore the possibility that by redshift 5, it has core collapse into a black hole C. Okay? So the time budget we have is just a 0.5 gigayears. It's a very short time. And here I show you contours of core collapse time on this concentration halo mass diagram. The way to read it is the following. 0.5 is here, 0.5 gigayears is here. So focus on the shape. Okay. First of all, you have an optimal mass regime. Okay. There's a characteristic mass at which you don't need super high concentration to core collapse in time. But that not super high concentration is still concentration of 10. The second thing you realize is that you really need very high concentration at least of order 10. And Andy used concentration 4 for your code disk calculations. So you may wonder, is concentration of 10 feasible at all? Okay. And by the way, this characteristic mass scale is just the consequence of velocity-dependent cross-section. So at the low mass end, okay, the central density is low, so there's no efficient self-scattering. At the high mass end, okay, the cross-section just drops dramatically. So whether or not concentration of 10 is feasible, we just examined this in cosmological dark matter simulations, the CDM simulations. Okay? And here, Zheng Haonan, my postdoc, is measuring the concentration distribution in the VVV simulation optimized for high Z mini halos. So we realize the concentration distribution at high Z is indeed has a median value of order 3 or 4, but it has a high concentration tail extending to 10, 20, all possible. So it's a log normal distribution with a median of 3 and a scatter of 0.2 dex. We verified it in using Guraft that Aaron Yan presented. And also we checked this in Thyssen HR, the dark version of Thyssen HR simulations, and all show very consistent results. So this tail is robust. So Andy, you can even try higher concentration values. And core collapse time, TCC, is just a part of the story. We also need to compare this timescale to the other important timescale, which is the look back time to halo formation, right? Because it's really about the time budget you have. You turn on the self-interaction clock once your halo forms. Okay? So you have to compare TCC, T core collapse, to T form look back time. Okay? And fortunately, we know how to compute T formation. That's very simple. We just apply extended projector theory. And in this time versus redshift space, I show you in the green band, just the T form formation time distributions based on semi-analytic calculations. The blue line here indicates the core collapse time. So whenever you see an intersection regime, there is a possibility of there's a feasible regime for core collapse to happen in time. So here I will keep concentration fixed in this movie. I will keep the cross-section choice also fixed. I just scan through this different mass choices, starting from 10 to the 6 solar masses all the way to 10 to the 10. Okay, see what happens. So there is an optimal mass range, as you can already anticipate, right? Between about 10 to the 6 to about 10 to the 8.5 solar masses, at which, again, so at which you can form black hole seeds in the early forming tail, okay? And that early forming tail only exists at high enough redshifts, at redshift about 9, 10-ish, okay? So you don't need to worry about producing too abundant black hole seeds. Okay? It only operates at high Z and only populate high C and the early forming tails. So we can put everything together. We can consider halo merger tree. We generate halo merger trees using prefactor formalism using my setgen code. We draw concentration for each progenitor halo branch. We keep the concentration fixed. We consider 2 time scales. We seed black holes. And we also consider very simple black hole growth and black hole merger recipes. And for black hole mergers, we just really consider very simple dynamical friction. And as Frank may talk about on Thursday, we don't need to worry about the effects like core stalling in the context of SIDM. So it's all very simple. At the end of the day, we have this. The red band is our model prediction. We have to choose a cross-section, but I emphasize that the cross-section that we adopt is not from fine-tuning. I will elaborate on that point. The diamonds here are observations, or rather inference based on observed luminosity functions. Okay, and the red band just captures the halo-to-halo variance of our model realizations. Okay, so about the cross-section choice, 30 centimeters square per gram and the omega of 70 kilometers per second. This is actually based on totally orthogonal local constraints based on rotation curve fitting. So we have a simple isothermal genes model that can predict ICIDM halo profiles. And we fit rotation curves. We fit the model to rotation curves. And we realize that in many systems, you have 2 solutions, one at the core building stage, one at the core collapse stage. But at the end of the day, we have this degenerate band as indicated by the blue region here, okay, in the cross-section parameter space. So this is sigma naught, this is the omega velocity scale. We can't break the degeneracy because we don't have data in the ultra-faint regime, as James talked about a couple of years ago, right? We really need to, if we want to rule out ICIDM, we need to probe the ultra-faint regime, okay? So this is how I chose the fiducial value of cross-section. I point my finger to here. Yeah. I essentially just point my finger to the middle of the blue band. Yeah. That's the cross-section. Of course, you can explore what if we change the cross-section. If we increase the rest frame cross-section by a little bit, we overshoot the low mass n. If we increase the omega, the velocity scale, a little bit, we overshoot the mass band. But I'm not favoring one cross-section choice over another because I don't even consider duty cycle. I don't even tune Eddington ratio, okay? So I'm just highlighting the flexibility of this model and also highlight the fact that we do have sensitivity of little red dot mass function to the cross-section, to the dark physics. So in principle, you can use this to constrain the dark matter physics. And to put our fiducial cross-section choice into context, so this is a cross-section constraint using Draco central density estimates that Oren Sloan worked on. So our choice is here, okay, within the feasible regime. And these 2 diagrams show you the cross-section models explored by modern-day state-of-the-art ICIDM cosmological simulations. This left one's by Turner et al. And the right one's by Eason. Okay, so our fiducial choice, as represented by the dashed red line, just sits in the right ballpark. So to summarize, I think I've showed you that little red dots can be seeded from self-interacting dark matter halos. And this process only works on the early forming halos, on the high concentration tail, and it only operates at high redshift, very reassuringly. We have used the SetGen model to present the very first statistical analysis of black holes seeded from ICIDM core collapse, and we can easily reproduce the observed mass function, and we explore the possibility of using this to constrain cross-section. And the fiducial cross-section is totally consistent with local orthogonal constraints from galaxy rotation curves. If I have another minute to talk about future related work, we are totally aware, okay, we are saying, okay, little red dots form a high concentration tail. So a high concentration tail indicates very strong galaxy assembly bias, halo assembly bias. And this is qualitatively consistent with the very preliminary observational results, for example, by Zhuangming et al., 25. We can also explore what happens to the baryons sitting in this core collapsing halo. We consider two competing scenarios. One is essentially morphological quenching. So you have a very deep and deepening potential. What happens to the gas disk? Maybe the disk is stabilized against the forming stars. Probably that's why we don't have a stellar envelope around the little red dots. Okay? But you may argue for the opposite. We may have feedback-free regime because the density is, okay, the potential is so deep. You can work out the free fall time, assuming, okay, cooling time is comparable to free fall time. You can compute the free fall time when the central density reaches 100 times the original scale density value. Okay? And that free fall time happens to be 0.5 million years if you assume concentration of 10, a ratio of 10. Okay? So that's shorter than the lifetime of OB stars. That's just a good condition for you to form nuclear star clusters. Okay, so with this, I summarize, show you my takeaway messages again, and happy to take any questions.
Okay.
So if you have a high sigma, we're talking about 50 centimeters squared per gram. I remember years ago, there's a constraint based on Lamb alpha forest. But if it's high sigma, it erases all the small scale power. Therefore, the flux distribution will be inconsistent with observation. So how does that square with the required value?
Are we talking about the same document? I'm not aware of a. Yeah, I'm not aware of a Lyman alpha constraint on the cross section, though. I may talk to you offline.
There was years back.
Yeah, okay.
Okay, Phil could connect, and I see a question in the back.
Thanks for the very interesting talk. So just correct me if I'm wrong, but you're sort of motivating this as the LRDs being these sort of like naked black holes inside these galaxies. I mean, but we see metal lines, right? And so if the metals are there, presumably something had to make them. So how does the sort of existence of a prior stellar population surrounding the black hole then fit in with the scenario?
So metals in the gas, right? You are referring to metals in the so I think with the last bit, I'm gradually leading to a picture where it's not totally exclusive with a little bit of star formation. It's totally, I mean, this is the ideal condition even for feedback-free starbursts, if you follow the density arguments. So I guess the main thing in this work, I think, is, although I frame it in the LRD context to better engage with observers, I'm pointing out an inevitable consequence of the ICIDM paradigm, that it has to form a lot of 10 to the 4, 10 to the 5 solar mass black holes in the early universe. But on top of that, you may have star formation.